Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. So here today in this video lecture, we will discuss about the topic taken from the subject, that is digital system design, and the code is KC 302 as prescribed in the AKTU syllabus. So here one of the complex topic which is really conceptual, and that is taken from the third unit, which is state diagram or state reduction. So if we go very smoothly and in a very precise manner, we can solve these type of questions very easily. So here first of all we should understand what is state diagram. So state diagram is also known as state graph, which is the pictorial representation. It can be represented in the form of a picture which represents the relationship between the present state, the input, and the next state, and also the output of any sequential circuit. So what are these four parameters? The present state, okay, PS, the next state, what was the input given previously, and then what is the output. So these four things can be represented state by state for any sequential circuit. Since sequential circuit we know very well, it is totally depending on the present state and next state. Okay, so the state diagram easily represent the relationship between the two states via figures. Now figure shows the state diagram of a MEALEY circuit, as we will see, in which the state can be represented by a circle. Here we will discuss the MEALEY circuit, right, and in which the state is represented by the circle, and also it is called as the node of the vertex, node or vertex, and the transition there. What is the state change from one state to another state, that can be linked by the directed lines connecting the circles. On the lines we can write the input and output. The directed line connecting the circles indicates from which state transition has been occurred to the next state. Similarly, the binary number inside each circle identifies the state represented by the circle. Let's say I am representing one state like this and another state like this. So this is one, this is second state, and here the transition is from state 1 to state 2, and here I can write this is the directing line, and these are the two states which can be represented by the circles, and the directed line can be labeled with two binary number. Let's say I write like this. So here this will represent my input and this will represent the output. Okay, the input value that causes state transition is labeled first, and the output value that occurs when this input is applied during the present state is labeled after the symbol, right. Here we can take one example for the MEALEY circuit, and state diagram is shown like this. Maybe in the examination you may be given this particular state diagram. So here I can see there are four states, 1, 2, 3 and 4. So first state is represented by 0, 0, second state by 0, 1, third state by 1, 0, and fourth state by 1, 1. Okay. Some directing lines are also there, as we can see from A to B. From A to A, from B to B, from B to C, from C to D, and from D to A, from D to D, from C to C, like this. These are the directing lines. So these directing lines are showing the state changes, right? So some values are also written on these directive lines, as we can see this. These are the values which have been, which are written on the directing lines, right? So one is representing the input and another one is the output. Same for all. Okay. Now coming to the state table. Once my state diagram has been made, so the state table can be written. So let us see how the state table can be written in this state table for MEALEY circuit. Okay. Now here we will write in the table first the present state. Present state may be A, maybe B, maybe C, maybe D. Very carefully, please see how the table is being written. Now for present state there will be next state. Okay. Present state there will be next state, and for next state there may be two inputs, x is equal to 0 or x is equal to 1, and for each input maybe there is the one output. Okay. So we will write, if input is 0, then what is the next state and what is the output? If input is 1, then what is the next state and what is the output? If input is 0, what is the next state, what is the output? If input is x is equal to 1, what is the next state, what is the output? So in the same manner we will write the table. So how the table will be labeled, that can be represented in the figure. Now just we should practice how to writing this thing. So okay, let us carefully write the table and then we will see the next part, which would be the reduction of the state table. So here we go. See, if input is x is equal to 0, next state is A and the output is 0. Here 0, next state is A and the output is 0. Input is 0. So we have written in the column of input x is equal to 0, and similarly if input is 1, the output is 0, right, and the next state would be B. So I have written B comma 0 and input is 1. In the similar way, let us see the C. If for C, the next state is D and input is 0 and output is also 0. And for C, next state is C and input is 1 and output is also 1. So here this is 1 1, for input to be 1, input to be 0, the next state is D and the output is 0. So similar way we can complete our table, state table, from the state diagram. Now let us once see what is the state table. The state table is the tabular representation of the state diagram. As we have already seen, it is a tabular representation of the same state diagram. The present state designates the state of the flip-flops before the application of the clock pulse. Obviously, all the flip-flops are clock pulsed and the application of the clock pulse will result in the next state. Now, both the state diagram and state table contain same information, and the choice between the two representation is a matter of convenience. So, in whatever way we feel right or we feel comfortable, we can either go for state table or we can go for the state diagram. So, it is very clear that state table and state diagram both are same, not different. We have written the state table from the state diagram itself. So, why the states are changing? The states are changing just because of the clock pulse given to the flip flops and the input provided to them. Now, here we have discussed the MEALEY circuit. Now, coming to the MEALEY circuit. So, MEALEY circuit, there is a slight difference, and the slight difference is that the state of memory element is specified by the value of its output. Okay. So, here as we can see, the A state, B state, C state and D state. Okay. Now, the output is written here. Oh, sorry. Input is written this thing on the lines. So, here the inputs are written. Coming to the present state, let's say the present state is A, B, C or D maybe. So, next state, some slight difference in the table writing technique also. If input is 0, okay, if input is 0, if the state is A and the input is 0, then output would be what? Okay, so here we have this A to A, input is 0, state is A and output is 0. Now, coming to the B state, output is 0 and input is 1 and next state is B. In the same manner, from B to B, input is 0 and output is 0. Input is 1. Next state is C and output is 0. So, here what is the observation? We can complete the rest part like this. So, observation is that state outputs are fixed. The outputs of any state is fixed. Let us say, as here for D and C, looking at the D and C, the output of D state is 0 and the output of C state is 1. So, the final output for x is equal to 0, C is switching from C to D. In that case, the output is 0. For x is equal to 1, C is switching from C to C and the output is also 1. Okay. So, in the similar manner, we can see the MEALEY circuit gives the output depending on its next state, D to A and D to D, right? D to A, the input is 0 and the output is 0. D to D, the output is 0 and the next state is D. So here one thing is clear, the state of a memory element is specified by the value of its output, okay, which may assume either 0 or 1. That means, please understand this line, the state of memory element is specified by the value of its output. Okay. So here in this Moore circuit can be easily uh, written and defined by its state table. Now coming to the state reduction technique. So here we have this state diagram, and in this state diagram we can see there one diagram is given which is having the 6 states A, B, C, D and E and F. So here we have so A, one state, second, third, fourth, fifth and sixth. So there are 6 states as we can understand from here. Now coming to the next part, writing the state table in the same manner as we did before. The present state may be A, B, C, D, E and F. Next state for input x is equal to 0 and x is equal to 1. The output for x is equal to 0 and x is equal to 1. So looking at this table, let us write for this thing B. So B is switching from B to F and B to E. For input 1 and for input 0, B to E for input 0, B to F for input 1. What is the output for input 0? For input 0 the output is 0 and for input 1 the output is 1. So we have written 0 and 1. Similarly, we can write all the state changes and the outputs for the next states for x is equal to 0 and x is equal to 1, where x is the input. By observing the table, we can see few state changes are the same. Few state changes are same in this BD01. BD01 is same. These two are same. And these two are same. EF01. EF01. Irrespective of this present state, the state changes are same and the output corresponding to the inputs are also same. So here what we can do, if A is same as C, it is whatever input I am giving to A, the changes in the states and the outputs are same for A and C. So I can write let A is equal to C, and I can also observe this EF01, I mean this B is equal to E. So I can write B state is same as E, because both are giving me the same state changes and the same inputs and outputs, right? So what to do next? So I can reduce this state table. Let us remove 2 rows from this state table. What should be the 2 rows which need to be reduced? First is this one. First is this one I will remove. Okay. and second I will remove this one. So I have fixed which rows I should remove from the state table. To remove, while removing, I should be very clear that I have to replace C with A and E with B. Okay. So what to do next? Now I have removed these two, BD01, A BD01. Correct? I have taken this, taken. So first row I have written as same, ABD01. Okay. Now second I will also take BEF01, taken. So BEF01, I will write BF01. So what is the problem in that? E I am going to remove. So I should write B in the place of E. So I will write BBF01. Okay. So I have written BBF01. Now next, I want to remove this also. I have already removed. So I will write DEB01. Check, E has been removed. So I will write DBB01. DBB01. Okay. Right. Next, this has been removed. This is taken. And E has been replaced with B. Now last, I have FFC01. But C should be replaced with A. So I will write FFA00. FFA0. Okay. This is how the state reduction has been done for this particular question. After reducing this state table, I can also draw my table, state diagram. I will redraw my state diagram. Now I have only 4 states instead of 6, A, B, D and F. So I have made A, B, D and F. Okay. So state diagram, corresponding inputs, corresponding outputs. A to B 0 0, A to B 0 0. This is the next state, A to B and input, and this is output. So I will redraw my diagram and state reduction has been done. Similarly, in the next example, we have taken one more example in which we can see there are 7 states A, B, C, D, E, F and G. Okay. So I have 7 states. I will write the state table corresponding. Okay. Corresponding to these changes, A to B, A to C, B to C, B to D, I will write for starting from A. So A to B and A to C. A to B and A to C for input 1, input 0, for 1 and 1 the output. A to B and A to C. Okay. Now B to D. B to D. B to D and B to C. Okay. So all the here B to D and B to C. Input for C is 1, for D is 0, output for C state change is 0 and output for D state change is 0. So we have completed the state table from the state diagram. While making this state diagram, again we have two rows as same, AF10, AF10. Okay. So if two rows are same, then I will definitely remove one. So I have decided to remove this one. So I will remove G and I will write E in place of G everywhere in my state table. This is how we go. So the table has not been reduced in a very big manner, but still we can see that this has been removed by like this. So we have obtained this ACB11, BDC00, CED, CED01, DED10, EAD10. So similar way I can write my state table and reduce this, and again we can draw the table. So instead of 7 states we have changed the 5 state, because again after replacing 2 lines were coming equal, this one EF10 and EF10. So I have removed this one also, and total 5 states have been selected. Now coming to the counters, there are 2 types of counter. First is asynchronous counter and second one is the synchronous counter. So the asynchronous, the counter is one output of one flip-flop is connected to the next flip-flop as a clock input. In the synchronous counter, all the flip-flops in the counter will work with the same clock. So all clocks are being applied to the flip-flops and all the flip-flops will toggle at the same time, right? The drawback of the asynchronous counter will be low speed, because one output being applied to next flip-flop and next flip-flop output will be applying to the another incoming flip-flop. So there will be a delay, and the flip-flops are connected with previous output. So here we can say that this is the ripple counters and synchronous counters. The ripple counters is same as asynchronous counter. So we have differentiated between the 2 counters. And one more important thing for the state changes, whenever the number of states we are defining for the counter, that is also known as modulus of the counter. The modulus of the counter is equal to the total number of distinct states including 0 when the counter starts counting. So here let's say if the first state is 0, then 1, 2, 4, 5 and 6. So what is the modulus of this? Count the number of states: 1, 2, 3, 4, 5, 6. So there are 7 states in total, and this is called as modulo 7 counter. Okay. So number of states are same as the modulus of the counter, and hence we will see the counters in the next lecture. Thank you.